MathSpec has developed some easy-to-use software applications to help identify unknown analytes from accurate mass fragmentation data. I'm Dan Sweeney from MathSpec Incorporated. In this video, I will show you how our MEP software compares a mass spectral dataset of an unknown analyte with thousands of molecular structures in Pubchem Compound that have almost the same mass. MEP is an abbreviation for mutually exclusive partitioning. To avoid repetition, I will assume that you have already seen the YouTube video Transform Mass Spectral Data into Viewable Models. In that video, an analyte of molecular weight 370 was partitioned into 10 sets of subfragments and subformulas. In this video, we will compare those 10 sets of partitions to a slice of 8,870 molecules in Pubchem Compound that have virtually the same molecular mass. For the transform demonstration, I used analyte 370-2115 from the above reference. This analyte was observed in 3 different surface water samples. Accurate mass fragmentation spectra were acquired for each analyte at both a high and a low collision energy. We will use the same data for MEP. Transform generates sets of subfragments and subformulas that are rough models of an unknown analyte. For many types of studies, for example, identifying reaction side products, the mass spectral data will take us only as far as these rough models. We need to then use background information to hypothesize possible molecular structures from these transform results. However, because the analyte with a mass of 370 was found in 3 different surface water samples, there's a high probability that this analyte is a known compound found in the massive Pubchem compound database of 124 million compounds. We will apply MEP. The MEP application first generates partitioning results like transform, but then it goes much further. A narrow mass slice of Pubchem is generated of all compounds close in mass to the analyte's accurate mass. MEP then compares the masses of subfragments from partitioning to exact masses of substructures of these compounds derived using systematic bond disconnection. MEP is mutually exclusive partitioning because each non-hydrogen atom must be allocated to one and only one substructure. You do not need to download or install this application onto your desktop because this application is available in the marketplace on Amazon Web Services. An instance is essentially a private server that has everything you need to run this application. The hardware, the Ubuntu operating system, the computer programs, and accessories such as Windows, Excel, and LibreOffice Calc templates for inputting and viewing the data. Your local computer can run either Windows or Linux. There's no big capital costs upfront or long-term subscriptions. You pay a small hourly charge while your instance is running. While stopped, there's only a very small charge for storage. These 3 EC2 instances were launched with our Amazon machine images in Marketplace that have everything needed to run. MEP runs in parallel using all 8 cores of a C8A 2X large instance type. I will not demonstrate how to set up an EC2 instance from the AWS Marketplace. Here is a link to a video on AWS that describes that. Now I have logged into Amazon AWS and I am in the EC2 dashboard. I will turn the MEP instance on Okay, it's running. To access your EC2 instance, you will need to use your organization's virtual private network and secure client software. Today, I will use WinSCP with Windows. I would use FileZilla with my Linux laptop. We need to first find the public DNS of the EC2 instance. In WinSCP, I need to edit the host name with the new DNS. We always use username Ubuntu for all three of our AMIs. Save that and log in. The SSH host key is a key pair, a public and a private one, that uniquely identifies an SSH server. On Amazon AWS, you can generate a key pair. You then load that the private key onto an EC2 server when you create the EC2 instance from our AMI in Marketplace. You keep the other key, the public key, on your local computer to verify that you are connecting to the intended EC2 instance and not some imposter. Right side of the WinSCP is the remote computer or the EC2 instance, and the left side is a folder in your local computer. In this case, I have a new demo folder I'm using. There are four folders in the Ubuntu directory. The Go folder is present because this software uses a Go language, also called Golang. The accessories folder holds the templates, and we use the Excel template in our YouTube video on transform, and we'll just modify that one today. Let us look at the workbook that was created with the transform YouTube video. We've already filled in the proper columns and parameters. This data input worksheet was also saved as a CSV file. Now there's two differences between the parameters for partitioning with MEP and partitioning in transform. In column J, MEP only allows fluorine to be excluded as a possible element. This is kind of handy for natural products, but it's not possible to exclude the other 7 elements. Secondly, MEP always allows odd E subformulas, even if it set false. So now I'll go to the worksheet Get CIDs. The advantage of using this worksheet is that when you find the CIDs within the mass range, they will be in order of relevance. Now, I forgot I need to get the molecular protonated molecular ion. Paste that in, and it will automatically know from the data input worksheet that it's positive ion mode and the error window is 3. And so we can calculate the upper and lower mass limit of the compounds in Pubchem that we want to get. And so this link of 8,870 compounds, it's called a catch key. and it's basically a temporary listing of compounds in Pubchem in that range. So I'm going to paste them in another window here. And this should match. So it's 8870. And these compounds are in order of relevance. So this insecticide is the most relevant compound close in mass to our unknown analyte. We need to download, and we want SDF and 2D SDF. So this might take a little time here. An SDF file is a kind of a continuous chain of compounds that are in mole file format. So we have each mole file is sort of an independent compound, and it's all chained together in one giant SDF file. Okay, so it's done. I'm going to copy that and go back to WinSCP and paste it. I'm going to rename this. So now we have the Excel file, which I should save. And we've got the CSV file, the same one that we created with the transform, and the SDF file, which is fairly large. Now I want to zip these two together, basically the analyte data from the data input worksheet and the large number of compounds. I cannot do that with WinSCP, so I'm going to have to go out. So I want to select the CSV file and the SDF file and send them to a compressed folder. I'm going to rename this analyte. And then I need to add a suffix .0. The .0 means to run all 8870 compounds. If I was in a hurry or something and I only wanted to look at the first 100 most relevant compounds, I could make this 100. But I would recommend running all compounds in that range. And that's what I'm going to do. So I'll close this now. Go back to WinSCP. And okay, here's my zip file. Go to input. And we're uploading from our local computer to the server on the cloud. Every 60 seconds or so, the MEP application will look for new data. And so if it sees a file in here that hasn't been run yet, it will transfer it over and start analyzing it. If you had let's say 5 or 6 compounds that you wanted to run at once, you can put them all in at once. It'll just run one zip file at a time, but it will keep doing them until there's none left. Now this is going to take, I've run this before, it'll take 47 minutes to run. So what I've done is, like on a baking show, I've already got one ready to pop out of the oven. So here we are. So let's open up the folder. Will get the name of the zip file. So here we have 3 Word files and a bunch of individual files. These each represent, we had 8,870 compounds listed in order of relevance, and these numbers are from 0 to 8,869 for the compounds. So these XX numbers are how relevant each compound was. If we go to partitions, it should be almost exactly the same as what we got when we ran transform. So I'm going to right click and open it up, and it will be in Word. And all this is pretty much the same. We're rehashing, if you will, the parameters that were used. It's compressed the 24 masses down to 12. It gives us some comments in here. This one, you could get up to 10 partitions. You won't get more than that. The partitions are listed in decreasing order of partition score. So this one, the 126. If we look at the last one, it's getting 110. So all the scores are pretty high. A higher scoring partition will explain a greater number of the more intense fragment ions. The subfragment masses are always listed in increasing mass from left to right, and the masses are in units of millidaltons times 10. If we look these over, we'll find that 5 of these 10 partitions have 5 subfragments, like this one here. 4 of them have 4 subfragments, and the one at the bottom there was only 3 subfragments. When you're comparing partition results to a molecular structure, the 5 subfragment partitions have the most structural resolution, and so they're the most discriminating. Now, the transform and partitioning will generate subformulas which can be added up to a whole formula. But I should point out that MEP, when we're searching the Pubchem database, it uses only these subfragment masses. So we're comparing subfragment masses to substructure masses. So now let's look at the results by size. So open this up, and let's blow this up. The number of matches is usually proportional to the size of the file. So now let's look at the summarized results. I'm going to copy this and go back to our Excel workbook. And there's a fourth worksheet that we haven't looked at yet. And I will paste special text in. And to fill this one down, it won't fill automatically. I go to one cell down and then go up and then pull down. And so now these are hyperlinks. So if we want to see, for example, the 199 was one of the more relevant compounds. So we can bring that up in Pubchem. And this is the structure. If we look at this, there are three compounds that actually had the same matches. So the 128, 42685, it matched 0, 2. These are the partition numbers that it matched. These are exactly the same. And the mass errors are the same. And this one up here at the top also. So it's giving the subfragment mass error between the substructure and the subfragment that was calculated by partitioning. And then there's a couple, number 9 is matching everything, it looks like, except this compound here, 1777, this is matching number 2 only. And I think there's one more, yeah, 5683, it matches number 9. So number 9 had only 3 subfragments, so that would have the least amount of resolution and more likely to get more matches. And the most resolving power is in the 5-cell or 5 subfragment partitions. So let's compare this color-coded partition 0 to the most relevant compound, which is the 128. And this is its match to partition 0. And so it's saying, it's giving here a list of what the substructure was in 128.42685 and what the subfragment mass was. So Pubchem CID 128.42685 matched partition 0. Here are the calculated exact masses of the 5 substructures of Pubchem CID 128.42685, where the 4 bonds that were disconnected correlate with partition 0. The masses were converted to integers as units of millidaltons times 10. Now, this is just one of the many ways to break up this compound, but this is the one that seemed to match. So the top row here lists the exact masses of the 5 substructures of the compound. The ordering of the masses is not the same, and so color coding was used to denote the pairs of corresponding masses. The partitions derived from the mass spectral data usually will vary from the exact masses of substructures by the mass of an integral number of hydrogen atoms. You can consider partitioning as a form of elemental arithmetic that helps to interpret mass spectral data. For example, the formula CH-2O and corresponding mass 259799 are needed in partition 0 to achieve elemental balance. CH-2O differs from the carbonyl group by the mass of 2 hydrogen atoms. The other two compounds that match partition 0 are exactly the same as far as the assignments. In addition to matching subfragment masses to masses of substructures, the second discriminating factor is the connections based on the fragment assignments. So over here, these were the subfragments and the assignments. And here it's saying that the 26 is connected to the 93, this 86 to the 105. We talked about this in the earlier YouTube video. The sums in white are essentially fragment assignments. Viewed this way, we were able to deduce some structural information about the analyte. For example, the 860480 sum as a pair of masses implies that the blue and cyan subfragments are connected directly. The 198 pair implies that the yellow and magenta subfragments are connected directly. The triplet mass at 224 together with the 198 pair implies that the 26 subfragment is connected to either the 93 or the 105 subfragment, but it cannot be a connection in between these two subfragments. And we can also deduce that the cyan subfragment and the red subfragment are outside masses because they can be lost without affecting the rest of the structure. The assignments of the 60 and 105 fragments as individual fragments do not really help as far as discrimination. So from the output of this CID number, it's giving some connection information based on the structure. So we can compare that to partitioning. We had pairs, so we said that the 26 was connected to the 60 and the 93 to the 105, so that's consistent. And from the triplets, we said that the 26 had to be connected to the 93 or the 105, and here it's saying that it was a 93. So this spatial information helps a lot in discriminating between compounds. Now, based on the MEP results, 3 compounds in Pubchem are consistent with most of the mass spectral data. However, it's important to realize that almost all structural information in this figure is in the mind's eye. Mass spectral data is ambiguous. Mass spectral interpretation is based on combinations of atoms, not permutations. For example, let's look at the cyan-colored moiety at 60.0681 Daltons. There are 6 ways of drawing a C2H8N2 substructure. Let's remove one hydrogen atom to connect the resulting C2H7N2 to the carbonyl group and the rest of the molecule. If we assume the connection to the carbonyl moiety is with one of the nitrogens, there are really 8 substructures possible because 2 of these substructures are not symmetrical. This demonstrates that even with only 4 heavy atoms in a subformula, it is not possible to elucidate a unique substructure just from the mass spectral data. The assignment of much larger subformulas to a unique substructure is virtually impossible from the mass spectral data. Therefore, the details of a structure derived from mass spectral data are always in the mind's eye. Thank you for watching this video.